All right, guys, let's go ahead and go over the warm-up for today, and then we're going to be getting into the notes, which kind of pick up where we left off yesterday and contain the rest of the information that you will need in order to answer the questions in your assignment 601.1, which hopefully you've already started. If not, you've got quite a few questions then to answer tonight. The other thing that you have for homework before we get into it today is the bumper RA. So your relevant application, your individual presentation is due by 11:59 p.m. tonight. Your calculations, which are done on paper, since they're done on paper, need to be turned in person, which means they need to be turned in by the end of the school day, preferably before you leave the class period, but you are welcome to come back by at the end of the day or even come in for tutorials after school today. Tutorials on Tuesday afternoons are with Mr. Guthrie next door, so if you do show up, that is where you will be. Let's go ahead and go over the warm-up. It says, Cedric pulls at a leftward angle to slow down a wagon rolling to the right. Is Cedric doing work? If yes, is his work positive or negative? If no, why is this not work? So I think this is a little easier if we have a picture, and I think yours has a picture. Okay, and so this is what it's referring to. So this has more information. It says, Michelle hopped in her wagon atop a hill and started rolling down and to the right. Her father, Cedric, caught up to her at the bottom of the hill and grabbed the handle, pulling leftward to slow her down. Okay, is that work? Is Cedric doing work on the wagon? Guys, I need y'all's attention up here. Okay, yes, I see nods. Yes, this is work. Okay, is that going to be positive or negative work? Negative. Negative, because he is applying a force in the opposite direction of the displacement of the wagon. Okay, you can also think of work as energy transfer, and by him slowing it down, which it says in the question there, because he is slowing it down, he is going to be causing energy to be lost from that system, that wagon. We haven't talked about energy yet specifically, other than to say that work is energy transfer, but if you slow something down, you're going to be losing kinetic energy, which we're going to be talking about in, I don't know if it's tomorrow or the next day, but in the next couple of days. Okay, but that is an example of negative work. All right, so let's hop into the notes for today. Please make sure you have submitted the warm-up questions in My Open Math, and we'll get through the notes, and then you should have some time to work on the assignment or on your bumper calculations if you have not yet finished those. So work as a dot product, okay? Whenever we talk about, and we've already looked at the equation for work yesterday, but anytime you're looking at an equation and you're multiplying vectors together, any two vectors can be multiplied using a dot product. And you guys theoretically learned about dot products and cross products at some point in math. I just don't remember when they did that or if you remember it. So let's just really quickly give ourselves a refresher. Because the work equation involves multiplying two vectors, force and displacement, the work is going to be a dot product, and I put a link here if you want to read more about dot products specifically, but we've already kind of talked about this without using the name. Okay, but it is a dot product because we're multiplying two vectors. What that means is that when you're multiplying those, you can only multiply their lengths when they point in the same direction. Okay, and we talked about this yesterday. Only the portion that is parallel is responsible for doing work. And so if you have an example like what is shown over here to the left, where you have force that is applied at an angle like in our warm-up, and your displacement is going to be, in this case, horizontal, then you can't just multiply the two numbers together. If your force is at an angle, you have to get the component of the force that is responsible for the displacement, and that's what we did yesterday. We just didn't talk about it, just wherever you want. We didn't talk about it as a dot product, but you don't just get to multiply that whole amount of force times your displacement. You have to find the component. Okay, and so when we look at our equation, it is a dot product equation. That's why when we wrote it out, we wrote out that work was equal to F times displacement times cosine theta, because that is what the dot product means. It means we're only multiplying those vectors when they're in the same direction. Okay, so we had to find the cosine of the angle to get the component, the x component in this case, that is in the same direction as that displacement. So again, it says, so we make one point in the same direction as the other by multiplying by cosine theta to find the component of force Fx that is in the same direction as displacement. We already talked about this yesterday. I'm just going over this vocab term. It's a dot product, okay, that we're looking at. So you can write it as F dot d or delta x for your displacement. And that is implying then that you would have to take just the component that's in the same direction. Okay, again, we talked about this yesterday as well, but when this man carries the box in this image right here, he's picking it up, and then once he's holding it, he's walking forward. That's the part I'm talking about when he's actually carrying it. This is not work because he applies an upward force to support the weight of the box, but his displacement is forward. Okay, and that's what you see down there where the force is upward, but your displacement is 90 degrees, is horizontal. And so that's not going to be work because, again, when we multiply vectors, we use that dot product. We can only multiply when they're parallel, and no component of that's parallel if you're at 90 degrees, if they're perpendicular to each other. Again, as a reminder, carrying something across level ground is not work because no portion of your force is parallel to displacement. You can also see this mathematically. Again, that equation, FD cosine theta, does anybody know off the top of their head what the cosine of 90 degrees is? If you have something at a right angle, what's the cosine of 90?
60. 30.
0. Okay. Guys, multiply by 0, what do you get?
0.
That's why you're not doing any work. You can see it mathematically as well. Okay, so if you have your force 90 degrees to your displacement, if you plug in that cosine 90, you're multiplying by 0, it's not going to be work. Mathematically, it's not going to be work by the definitions we gave. There's no way you're going to get a number unless you just don't plug in cosine 90, okay? And then, of course, you would get a number and it'd be wrong. But again, you can only multiply the component that is parallel. There is no component parallel, 0. Okay, cosine 90 is 0. Okay, so that's why you get 0 work with an example like this. Again, we're just kind of reviewing some stuff before we add a couple new things on here, but work can be negative. A dot product gives a scalar answer, and scalar values don't denote direction. However, as you learned yesterday, work is energy transfer. Okay, and you can have a change in energy that is negative. You can have a system lose energy, you can have a system gain energy, and so you can have a sign here because you're talking about the change in that energy. Again, work is positive when the applied force is in the same direction as the motion because it adds energy to the system. Work is negative when the applied force is opposite that direction of motion because it removes energy from the system. Okay, and so again, we talked about this yesterday in terms of when my force is in the same direction as my displacement, it's positive, but it's because you're adding energy in that case. And just like the second one says, okay, whenever your force is opposite your displacement, you're removing energy. That's why you get a negative value for your work, because work is the change in energy of your system. And again, we haven't talked directly about energy. We're kind of referring to it here, but I know you guys know at least something about energy from junior high, from those science classes. We're going to get into it more again later on, but for now you can just write this down. Okay, so again, you can have negative work if you have a situation where the force that you're applying removes energy from the system. Okay, or the force is opposite the direction as the object's displacement, which of course would remove energy from the system. Friction was the example that I gave you yesterday. Okay, because friction always applies the force opposite the direction of the object's motion, and therefore it would always remove energy from your system. So again, just some more examples of positive and negative work if you weren't too clear on it yesterday. I've got a few on my screen here. It says, in pulling a box of books along a rough floor at constant velocity, I do positive work on the box. That is, I put energy into the system because the force I'm applying and the displacement of the box are in the same direction. However, the force of friction opposes that displacement. Always, by the way, force of friction is always going to oppose that direction of displacement, direction of your motion. Okay, so that force of friction does negative work on the box. So both me and the floor, friction from the floor, would be doing work on the box. Therefore, because we're both doing work, we can have net work, okay, where you have the total amount of work done on the box. Just like we had net force, we can have the total amount of force done on the box between the force I'm applying and the force that the floor is applying. Because it says up here that it moves at constant velocity, I know that would be a situation where I would have balanced forces, meaning that if I'm applying 100 newtons of force, then friction's applying negative 100 newtons of force to give me a net force of 0. And if my net force is 0, so is my net work. Net work is the total of my positive work and the negative work done by friction. When the velocity is constant and the forces are balanced, the net force is 0. Thus, the energy of the box does not change and its velocity remains constant, and the net work done on the box is 0. If you see constant velocity, net force 0, net work 0. Okay, they're both going to be 0 because you don't have a change in the motion, and therefore you don't have a change in the energy. Yes?
On the open math thing, it says choose all situations below that show no work. Mm-hmm. So would a jogger running upstairs at a constant speed be no work?
There is still, you do still have work occurring. The jogger would still be doing work and lifting himself. But if it asks specifically about net work done, then it would be 0. Like in this example, I'm still doing work on the box. It's just that the work I'm doing is being canceled out by the friction, the work friction's doing. Doesn't mean I'm not doing work. It just means that the net work is 0. All right, so let's look at some more examples. This one says, when a ball is dropped from rest at a height of 3 meters, describe the work done on the ball by gravity and by air resistance. So I don't have a ball up here, but if I drop something, okay, if I drop this, okay, what direction is the force gravity acts on my pen? Down. What direction is the displacement of my pen? Down. If my force and my displacement are in the same direction, what do you know about the work done by gravity? Because gravity does apply a force. Okay, so if they're in the same direction, what do we say work would be? Positive or negative? Positive. It's adding energy. Okay, again, we know that because I just saw it move. It wasn't moving and then it started moving. Okay, so obviously I gained some energy in my system. I have positive work done here. I added energy. Okay, or I didn't, gravity did. Okay, gravity added energy to that system. What about air resistance? There is air resistance in this room. Okay, what direction would air resistance be acting on my pen as it falls? It's basically friction with air molecules. What direction does friction act? Opposite. Always opposite, right? Okay, and so if I drop this, and it's not super noticeable with a pen, but if I got like a feather, you'd be able to see it much better. Okay, that force of air resistance is up, but what direction is the displacement of the object I dropped? Down. So what is my work, positive or negative? Negative. Air resistance is trying to slow it down. It means it's trying to remove energy from the system. It's a negative work done by air resistance. Okay, so that's kind of the thought process you're going to have to go through to answer questions like that. Okay, when the ball is dropped, it speeds up as it falls. Is the net work positive, negative, or 0? If it speeds up, not 0. Right? If we have a change in our velocity, that means we have a net force. And if we have a net force, we will have net work. Okay? Because you can say that net work equals net force times displacement. The same equation from yesterday. You're just using the net values now. Okay? And so if it speeds up as it falls, okay, right here, then I know that I would have negative acceleration toward the ground. Okay? So I have acceleration toward the ground, which means I have a negative net force. My net force is downward. Okay, and I have negative displacement because it fell, it went down. Okay, and since those are in the same direction, I would have positive net work acting on the ball. And again, I think it's easier to see if you look at a free body diagram and think about the forces there. Okay, your force of gravity would be larger than your force of air resistance, and so your net force is downward, and therefore your net work, since your displacement is also downward, would be positive. Okay, so you can just find your net force, and that will help you determine your net work whenever you're doing calculations. If there's more than one force. Obviously, if there's just one force, Your net work is the work done by that one force. But if you have two or more, you'll have to do something like that. Okay, so here's another example. It says a 2 kilogram ball initially moving at 3 meters per second comes to a stop over a frictional surface as shown. If the force of friction is negative 8 newtons and the ball comes to a stop over a distance of 1.2 meters, what is the work done by friction? Again, work is force times displacement times cosine of my angle. I don't have an angle. Everything here is horizontal. Okay, so I don't have to worry about multiplying by cosine of 0. I could, but cosine of 0 is 1. Okay, and so I just need to multiply my force times my displacement. The force it's talking about here is the force of friction. The displacement is the distance it says that the ball travels right there. And so I would take my force from the question, negative 8. I would multiply it by the distance in the question, the displacement, 1.2. So it's going 1.2 meters to the right, but the force is acting to the left. So my signs are opposite here. And of course, that's going to give me a negative amount of work mathematically. But I already knew it was going to be negative because friction's acting opposite the direction of my displacement. But you get a negative number mathematically as well because you're multiplying a positive times a negative. Negative 9.6 joules would be your answer to this question. Does anybody have a question about that? Okay. Again, why is it negative? Friction is opposite the motion, so it's the force is opposite your displacement. You could go with that reason, or you could say it causes the ball to lose energy. It's slowing down. Okay, so it's losing kinetic energy. And again, we're going to talk more about kinetic energy over the next few days. All right, a 78 kilogram man climbs 3 meters up a flight of stairs. How much work does the man do against gravity? Again, when you do work, you do it against something. Okay, and so what is the force acting on him? What is he working against? What force is he working against? Gravity. Okay, if I want to lift myself, how much force do you think I have to apply?
Your weight.
My weight. I have to apply force equal to my weight. Okay, to lift myself up some stairs. You do too. Okay, and so we could figure out the force acting on him. It's going to be Fg. Okay, and he's going to be applying, so Fg is down, he's going to be applying an upward force that's equal and opposite if he's moving up the stairs at constant speed. Okay, but the force here would be his weight. Okay, so that normal force from the stair would equal Fg, which would equal mass times gravitational acceleration. It says in the question that he's got a mass of 78 kilograms. So if we multiply 78 times 9.8, we get a weight of 764.4 newtons. That's the force pulling down on him, and therefore that's the force he is applying in order to lift himself up the stairs. He has to lift his own weight. So 764.4 newtons would be the force. That's not the answer to the question, though, because the question doesn't ask for the force. It wants to know how much work he does. Okay, and so the work he does is force times distance. We need to take that distance. Now, I don't care about the distance he goes sideways, right? Because that's 90 degrees, okay, from that force. All I care about is his upward distance. So all I care about is his height, how high he climbs. Okay, not his physical height, but how high he climbs the stairs, which it says is 3 meters upward. I don't care about forward, I care about upward. Okay, so I'm going to take that force, I'm going to take that distance, and I'm going to multiply them. Okay, and they're both upward, so he's going in the same direction as his displacement, so my work is positive. Again, mathematically, you're going to get a positive number if you multiply positive times positive. In this case, 2,293.2 joules. Questions about this one? Okay. All right, here's one at an angle. So if you're not taking notes yet, you might want to pause for a moment and copy it down, because I know how much you guys loved forces at an angle. Okay, and they're coming back. I know, it was your favorite. Y'all were like, please give us some more trig. We miss it. Okay, all right. So here is a question that, again, I would recommend that you write down. It says, a man applies 214 newtons of force to push a lawnmower at an angle of 38 degrees below the horizontal as shown. If he pushes the lawnmower 10.5 meters across his yard, how much work does he do on the lawnmower? Okay, so again, in order for us to calculate work, we really need to find this component right here, because we can only use the component of his force that is parallel to his displacement. His displacement is across the lawn. It's not down through the ground and forward. It is just to the right. And so we would use cosine, okay, again, SOHCAHTOA cosine, ca, right here. And we would say that the cosine of 38 degrees equals the adjacent side, which is fx, divided by the hypotenuse, which is 214. Okay, and if you rearrange that, you get this. 214 times cosine 38, okay, which is 168.634 newtons. So that is the component of his force that is parallel to his displacement. That's the only part of his force I care about. You're not going to use 214. You are going to use 168.634. Okay, don't use that whole thing. Use just the component. Okay, if you instead had used FD cosine theta, then all of this math would be done inside this equation, which would also work. But since I already did it, I'm going to go ahead and take that force component that I found, 168.634. Okay, and again, that is F cosine theta times D, 10.5. And when I multiply those, I get a work done of 1,770.7 joules. Again, joules is the unit that you will use for work. Okay, so if it's at an angle, you're going to have to find that component. Okay, again, if you plug it in to the equation FD cosine theta, then you're doing it all in one step, and that's fine too. Or you can find that component using F cosine theta and then plug it in and multiply by D. Either way. Does anybody have a question about this calculation? Again, you'll hopefully, once you practice it on your own a little bit, you'll feel more comfortable with it. All right. Or use the dot product equation. You can do it all in one step. There it is. 214 times 10.5 times cosine 38 is the exact same answer. Either way will get you there. Okay, you can do it in one step or you can do it in two steps. Why is it positive? Again, the force he's applying is in the same direction as his displacement, or at least some component of it is, and because his displacement and force are in the same direction, you will get a positive value for work. All right, here's two more questions, same scenario. Okay, if the net work on the mower is 1,200 joules, find the work by friction. We just found his work. The work that the man does, 1,770.7 joules. But if the net work is 1,200, again, we're going to do net work calculations just like we did net force calculations. Net means total. So the total work on the lawnmower would be equal to the work done by the man plus the work done by friction, keeping in mind that the work done by friction is going to be a negative number. Okay, so if we plug in our values here, it tells us in the question that our net work is 1,200. Here's the work done by the man. I'm solving for this one. I'm going to get a negative number because when I subtract 1,770.7 from 1,200, I'm going to get negative 570.7 joules, and that will be the work done by friction. Okay, so you can find your work done by friction from your network, or if I had you work backwards, you could have found the network if we gave you the work done by friction. Okay, what is the force of friction of the mower is the next question. Well, if you have the work done and you know the distance that the mower was pushed, you can find the force because your work equation looks like this. Okay, so your work done by friction would equal your force of friction multiplied by that displacement. Okay, my force of friction is negative 570.7 and my displacement's 10.5 meters. It's in the question. So if I substitute in, I get this. And I can solve for my force of friction by dividing both sides by 10.5, which would give me negative 54.35 newtons as my force of friction. So again, we can add lots of extra steps in here. Okay, you already know that. I know you know that because we've been doing it every unit. We keep bringing old stuff back and we have more and more steps that we can do. And the same thing applies here. Okay, you basically can use any equation from the entire year in this unit to solve the problems depending on the information that I give you. All right. That hopefully gets you ready to finish all those questions in there. We should have covered everything that you need now. in order to answer the questions in the assignment 601.1 work problem set. That is due by 11:59 p.m. tonight, and you are welcome to work on it for the rest of the class period today. You guys have 25 minutes or so. So you've got quite a bit of time to work on that. In addition, your RA is due today. Before you leave school today, I need a physical copy of your group's calculation data sheet. Okay, that's on your own notebook paper, but I need it from you before you leave. If you don't turn it in at the end of class, you need to come by before you leave school. Digitally, you need to turn in your individual posters. So part of it's online, part of it's in person. If you have questions as you're working through the assignment, or if you have questions on the RA stuff, please let me know.